Hi, my name is Noralia Abdulabdiskrain. My metric number is DD210011. So I'm going to start my group presentation by explaining about introduction. So control engineering involves designing and optimizing systems to manage operations, focusing on accuracy, stability, and response time. These systems often combine mechanical, electrical, or hybrid components to regulate device or process. There are two main approaches, which is traditional and modern methods. For our project, we focus on managing temperature in heat exchangers, particularly water tube boilers, which is these boilers use a drum boiler to store steam and control vapor. The drum helps separate steam from water, ensuring proper pressure and temperature conditions are maintained. And the main goal of the project is to analyze how the drum boiler handles temperature regulation. We will reduce the system to a simpler block diagram and evaluate its stability. MATLAB will be used to assess the frequency and temporary response of the system. So for the objective, in this project we achieve to understand the operation of the drum boiler, and the second one is to implement an automated PID temperature control system for a drum boiler, and the third one is to analyze and enhance the automated system. And the scope of work is, the project scope is limited to the following, which is the first one is complete mathematical computation for the drum boiler, and the second one is to study compare step response, root locus, port, and proportional integral derivative, which is PID controllers. And the last one is using MATLAB for simulation tasks. So I'm going to pass this presentation for the next group members.
Assalamualaikum, my name is Zini Hadrabati Zulkarnain. So I would like to proceed our group presentation with an overview of the literature review. So a little bit about our literature review is first thing first, the precise drum boiler temperature control is vital for safe efficient power plant operations. This is because it can create major operational risks which include thermal stress and material degradation and system failures. So the deviations here that we're talking about is the temperature deviations, and the temperature deviations can cause thermal stress, and this will give an overall system as a failure. And also we also gain some PID controllers information that are known for their simplicity and reliability that are widely used with modern optimization techniques like genetic algorithms, enhancing performance by addressing nonlinearities and delays. So in PID system, the Ziegler-Nicholas and Cohen-Cohen traditional methods establish the initial PID controller parameters, yet modern optimization are also being used to allow enhanced precision. So last but not least, the advanced PID methods such as cascade and feed-forward control improve system stability and accuracy as an overall. So a little bit about the factors that will be affecting the accurate measurement of drum boilers. So first thing first, it is about the sensor calibration and maintenance that are crucial for reliable readings. And next, we have the environmental factors like temperature variations and vibrations that impact sensor performance as an overall. Last but not least is the system disturbance such as load and feed water fluctuations introduce noise requiring noise reduction techniques like digital signal processing for reliable measurements. So next, I would like to present the types of boiler drum level control. So the first one we have here is the single element module, and the second one in the diagram we have the two element drum level controller, and the third one is the three element drum level controller. So I would like to start with the first one, which is a single element module. We can see from the picture itself, it have feed water valve and also drum level. And it uses a single element system with a feed water valve and drum level transmitter. And the controller compares PV with set points adjusting the feed water flow to maintain drum level. And the second one here in the diagram, you can see that it adjusts feed water flow using steam flow and drum level measurements, refining adjustment with feedback to account for blowdown losses and measurement errors. Last but not least, the three-element drum level control strategy is used when feed water systems are unstable, relying on drum level, steam flow, and feed water flow to manage variable pressure difference and unpredictable steam demands.
My name is Nurina Safia, matrix number DD290034, and in this presentation, I will explain the concept behind open loop and closed loop system. The open loop system models explain how the system naturally behaves without any feedback mechanism. It combines the dynamic of the process, actuator, and sensor, which work independently to produce the output. The process is represented as a first order system with a delay, described by the transfer function as shown, where n is the final output value, m is the step input, t is the time constant, and td is the delay response. The actuator and sensors are modeled separately. These components are then multiplied together to form the complete open loop transfer functions. This represents the system unregulated response to an input, where the output depends entirely on the individual dynamics of the component. On the other hand, the closed loop system introduces feedback to ensure the system achieve the desired performance. Feedback continuously monitor the output, compare it to the desired value, and adjust the input to reduce any error. This configuration allows the system to self-correct and maintain stability even when disturbance occur. The closed loop transfer function is derived by adding a feedback loop to the open loop model. The feedback mechanism makes the system more robust, providing greater control and stability compared to the open loop system. To make the equation practical, we substitute the given parameters into the derived transfer function. For both open and closed system, we substitute n equals to 46, m equals to 50, td equals to zero point 0.5, t equals to 29, k equals to 0.16, and lastly tau equals to 1. This simplified transfer function provides a clear mathematical representation of the system behavior in both open and closed loop configurations. The open loop models reveal that the system unregulated response, while the closed loop model demonstrate how feedback improves performance and stability.
My name is Nadira Betty Momaris. Today I want to talk about result and discussion. And my metric number is DD210058. So, the step responses of the open loop and closed loop system show clearly differences. The closed loop system has a faster rise time of the 3.59 second compared to 6.18 second for the open loop system. So its peak amplitude is lower, 0.210 versus 0.433, indicating better control. Additionally, the closed loop system stabilizes quicker with settling time of 8.96 seconds compared to 11.2 seconds. For the open loop system, this highlights the closed loop superior speed, precise, and stability. So for the root locus graph for both systems share a similar form or pattern. So in the open loop system, the poles are positioned at negative 1.73 plus 3.47i and negative 1.03 negative 3.47i, located symmetrically on the positive and negative side for imaginary axis. So in contrast, the closed loop system has its poles at negative 0.761 plus 5.91i and negative 0.761 negative 5.9ii, indicating a shift towards the imaginary axis and reflecting change in the system dynamic. So for plot diagram are effective tools for analyze frequency responses with separate magnitude and a phase plot on a logarithm scale. So for the open loop system has a peak gain of 382 dB at 1 multiplied 10 power of negative 20 rad per second, while the closed loop system achieves 1.65 dB at 1.42 multiply 10 power of negative 12 rad per second. So in terms of stability, the open loop system is stable at 0.105 rad per second with a phase margin of 64.1 degrees and a delay margin of 10.6 seconds in second. So the closed loop system is unstable at 0.372 rad per second with a phase margin of negative 62.2 degree and a delay margin of 14 seconds. So this result emphasizes the open loop system better stability compared to the loop system, closed loop system. The Nickel chart is a powerful tool for analyze feedback system, stability and frequency response by plotting open loop gain against the phase characteristic. So for the open loop system, the peak gain is 399 dB at 1 multiplied 10 power of negative 20 rep per second, while the closed loop system has a peak gain of the negative 19.7 dB at 6.54 rep per second. And both systems demonstrate stability through gain margins. So for the closed loop system has 35.1 dB at 2.15 rep per second and 33.7 dB at 7.64 rep per second, while the open loop system show 2.34 dB at 0.905 rep per second. Additionally, the open loop system exhibits a phase margin of the 12.5 degree and a delay margin of 0.28 second at 0.782 rep per second. So for the further confirming stability, this insight highlight the Nico chart importance in evaluating stability and performance in feedback system. According to Nyquist's principle, an analog signal can be accurately recreated if the sampling rate is at least twice the highest frequency, preventing distortion. The Nyquist diagram for both systems show that they stay stable across different frequencies. The open loop system has a peak gain of the negative 16 dB at the 2.26 multiplied 10 power of 0.8 rad per second, while the closed loop system has a negative 17.7 dB at 1 multiplied 10 power of 20 rad per second. So for the both systems are stable, with the open loop system showing a gain margin of the 31.8 dB at 0.0938 rad per second, and the closed loop system showing 36.6 dB at 2.95 rad per second, confirming their stability over their frequency range.
In conclusion, this project successfully used MATLAB to analyze and improve an automated control system. By applying techniques like step response, root curves, plot diagrams, and PID controllers, we gain a better understanding of the system behavior. MATLAB was essential for modeling and simulating complex systems. The project helped identify and solve key issues improving performance. It also highlights the difference between open loop and closed loop systems, emphasizing the importance of feedback for stability and control. Overall, this project improved our MATLAB skills and provided valuable insights into control theory, setting the stage for future advancement in automation. That's all from us. Thank you.